morning, this afternoon, evening, morning. Hopefully you can all hear me okay. If someone could just give me a thumbs up or pop something in the chat to let me know that that we're all good with that. And we'll make a start on today's session. We'll just give everybody a few minutes to come and join in. So hello to everybody. My name's Adam Taylor. And today we're going to be having a lot of fun with MicroBlaze and with PetaLinux. Everything I'm going to do, you should be able to do on any AMD FPGA board. I'm going to put a link into the GitHub repo that I have created. I'm going to put that there now, so everyone should be able to see that. And if you go there, you'll find all of the slides, everything that you need to go away and to recreate this and to build this and hopefully to get working with it and to follow along if you want to follow along. It's going to be quite a good session today. Hopefully, I've got a couple of questions in the poll as well that I'm going to make live. So if you want to take a look at those, please do, and we'll see what people are thinking of it. So just to give you a quick overview of what we're going to do today, we're going to create a MicroBlaze processor. We're going to validate that. Then we're going to build a embedded Linux solution using PetaLinux and create a simple application and debug it. You can probably see a little white thing over in my corner, just behind my finger there. And that's what I'm going to be targeting today. It is the RTA7. It's connected to my Linux build machine, which is the machine underneath it with all the colorful, nice lights going on and off. And what we're going to get eventually when we've created our application, I've plugged a simple PMod into it. So what we will see eventually is we'll see an application like this where we can track it on our oscilloscope and just see it as it's just writing a ramping waveform out over the PMod. This should hopefully take us about 2 hours or so. Maybe we'll get through it a little faster. Maybe it'll take a little longer, but normally it takes about the time that we thought it was going to take. If you get any questions, please pop them in the questions tab, and I will try and keep an eye on it and go through and answer them as we're going. Obviously, I'm just one person on my own, and I'm going to be talking quite a lot and driving Vivado and PetaLinux and stuff. So if I miss a question or something, please put something in the chat and say, "Hey, Adam, go look at this." But I'll make sure that at the end of this, I run through and do it. It'll all be available on demand as well at the end of this. So if you've got a link to it, you can go back and watch it, and the recordings will be made available to everybody that registered but missed it. I'm glad you like my lab. I've spent most of this afternoon tidying it up to make sure that it didn't look too messy. So what I'm going to do is I am going to start this show on the road. I'm going to flick and message out, and that's a good point, Sean. You know, if a lab's not messy or even working. But I've had far too much of a productive day today. I've had a really good day. We've been developing a little. I'll just show this now because I'm quite proud of it. We've been developing a little Kriya SOM module carrier card, and I've managed to get that all up and running and validated. So it's been actually a really good day today. So we're going to make a start. I'm going to switch over and show you the slides and minimize my ugly mug because I really do have a face for radio. So we're going to get a start on this. So like I say, we're gathered here today to try and work through and learn how to create a MicroBlaze processor that runs PetaLinux. And this is following on from one of our sessions that we had last year, where we sort of talked a lot about the MicroBlaze and how to create MicroBlaze applications. So our objectives for today really are we're going to create this MicroBlaze processor system. We're going to use Vivado for that. I've used Vivado 2023.2 for this, but I've also done a similar thing on my Hackster in a slightly earlier version of the tools as well. We're then going to create we're then going to create a PetaLinux project for this MicroBlaze. And once we've done that within PetaLinux, what we're going to do is we're going to add support for simple things such as SPI and I2C. And then I'm going to show you how we can connect to it and we can develop software and debug software applications using Vitis. And then we'll boot it all on the board and hopefully it will all run. So yes, someone was just asking if this is going to be recorded. And yeah, it is. Obviously, it will be recorded and you'll be able to take a look at it later on. So when it comes to doing this, like I said, I'm using Vivado 2020 3.2 in this, and just with everything, I'm using this completely across the same version across all of the tools and all of the Vivado, the Vitis, and the PetaLinux that we're running. I'm using it, as we said, I'm using this on my Linux machine that you can see behind me, wherever it is. I'm not very good at this. The brightly coloured one behind. You don't need a Linux machine to go through and to create the Vivado design, or even to do the Vitis software development and software debugging. You do need one to create you do need it to create the PetaLinux image though. And I have put the PetaLinux image is all available on that GitHub link I shared if you look up in the chat there. If you don't have a Linux machine, you can create a virtual machine and install Linux on that. And there's a link to a Hackster project there that shows you just how to create a virtual machine and run Linux on it if you need to do, if that's what you need to do it. So let's jump in a little bit. I'm not a huge fan of sort of death by PowerPoint on these presentations, but there are a few things that I want to run through and just set the baseline and make sure that we all understand what we're working with and what we're doing. Obviously, MicroBlaze, it's been around a fair while. I struggle to think of an FPGA design that I've done recently within the last sort of 5 or 6 years, maybe 10 years or so, where I've not put at least one MicroBlaze in it to do something at some point in time. Maybe even if it's just initially to help me test the board out or get the board working, that MicroBlaze processor has been being placed in there. It's a soft core processor that is instantiated on the top of our logic elements in the FPGA. And when we come to look at this, it's actually a Harvard architecture, so it has a distinct instruction path and a data path, and it's really flexible. I don't know how many people have used this that are attending, but it's one of the most flexible solutions there is. It can come in a very small, almost embedded type little processor called the MicroBlaze controller system, and that's really quite tiny. And then we can have the solution to scale in there, so we can have sort of embedded class things where we've got slightly more performance, where we put bare metal or real time on them. And in this instance, we're going to create an application class one where we're going to run embedded Linux on it. And you can create you can create triple modular redundant solutions on this. Typically, Jonathan, when you create TMR solutions, they run from their own block RAM, and you would do some voting between the two. Obviously, however, it is actually possible to do that and share the application, and the application's running in DDR, and share the application between the three. In that instance, it should be able to run with PetaLinux. I've never tried it actually, but I'm now writing a mental note to myself that I should put this on the list of things to try and do. What you can see in this diagram here, the important thing for us is the elements that are grayed out. They're completely optional. The non-grayed out elements are the basic element of the MicroBlaze processor. And today, as you would expect, because we're creating an application class processor, we're going to be using a lot of these optional features, particularly the memory management unit, the data and the instruction caches, and things like that. And if you ever want to see how bigger impact the caches and the barrel shift and the multipliers and such like can have, a look. I did about maybe 6 months ago now, I did a project on Hackster where I looked at the different optimizations that these could do and the performance that these would lead to and give you. So it's really quite useful to go through and do that. That's really all I'm going to say about the MicroBlaze. We talked about it a lot. Last time. Obviously, we're going to be connecting things to the AXI interfaces making this all work. One of the things that I do want to get going and do want to do with this is we want to talk a little bit about Petalinux up front. So Petalinux, it's not strictly a distribution or anything like that. It's basically a build system. It's a set of tools that allow us to build an embedded Linux solution for our target devices, and that could be anything from a MPSoC to a Versal to a Zinc 7000, and of course today is we're talking about a MicroBlaze. It's really simple. There are just 6 commands, and I don't think I've ever used actually the PetaLinux util command, but there are just 6 commands that we can use, as you'll see, to create and build a project. If anybody else can confirm that on the sound, we'll take a look at it. If not, then I think everything's showing okay on my side of things. Okay, maybe it's just their connection then. So one of the nice things about Petalinux, obviously, is that it basically uses Yocto, and it wraps around the from 2016.3 version. It wraps around Yocto and gives us a nice build system around that. And if we want, we can even emulate it using QEMU on our processor. So it works. It works really well. I think it would be good now to take a little bit of a look at some of what kind of comes with it and what comes with Petalinux. And I think it's really, it gives us everything that we need. So it gives us all of the source code. Most of it is kind of open source, apart from a few sort of hardware drivers. And it pulls in and it fetches all of the Linux kernels, the sources, the libraries, and along with the traditional Linux embedded applications and utilities. One of the really nice things about it, though, is we can pull in other layers and other elements and drivers if we need to from it. Obviously, today we're not going to. We're going to go with the fairly straightforward and fairly sort of standard flow. We're going to modify our root file system a little bit, but we're not going to do anything too exotic just due to the time that we have available, really. So what it's going to give us is going to give us everything we need to get going with our system. So it's going to give us literally everything we need. So it's going to give us the bootloader, the first stage bootloaders. If there's any trusted firmware, which there isn't for our MicroBlaze, then it will also generate that. We will see. The really important thing about this is we're going to create a design in Vivado, and then we're going to pull that design into Petalinux. And what Petalinux is going to do is it's going to work out and automatically detect what drivers are needed for those Vivado IP blocks and include those within the Petalinux build. It's going to do that, as you'll see, by using things with the device trees and creating the device trees. We're going to make some little modifications to the device tree, but it should be relatively simple. In fact, in some instances, when we get over to Linux side, because it does a lot of fetching from the internet and things like that, I'm going to do a little bit of a Blue Peter and switch over to the kind of the here's one I built earlier approach, just to make sure that we're not sat waiting around for a long time while we're downloading things. I'm a big fan, actually. Like, I'm a traditional FPGA engineer. I cut my teeth using VHDL and Verilog and learning like that. And since the introduction of the Zincs and the MPSoCs and MicroBlazes and things, I've had to learn sort of embedded software and, of course, Petalinux. I'm actually quite a big convert and a big fan of Petalinux. It makes a lot of things really straightforward and really simple to get up and running with. If you get stuck with anything, or if there's any issues with anything in terms of Petalinux, then user guide 1144, it really is sort of like the golden reference guide for not only installing it, but working with it and creating it. And it'll give you much more than that I'm going to talk about now in the next hour and 45 minutes or so. There's also kind of key elements to this as well that we're going to look at. If you want to look at more about sort of Petalinux as well, then we did do, I think about 18 months ago now, we did do a specific just one-on-one sort of Petalinux embedded workshop as well. So it's going to give, like I say, it's going to give us everything. It's going to give us everything we want to get going with and creating our application. So I'm going to skip over to this, and I'm going to show the build flow now. So the build flow that we're going to go through is very simple, and this is going to be nice and straightforward for us. So we're going to design our software in Vivado. We're going to export it from Vivado just like we would normally do. So we're going to capture the design. We're going to, thank you very much to the person that just put the user guide in the chat. We're going to capture the design, and then we're going to generate the bitstream and export the bitstream from Vivado into that XSA. Once we've got the XSA, we're going to come over into the PetaLinux world. We're going to create the project saying that we're targeting a MicroBlaze processor, and that's going to create as a template project. Once we've got that template project, we're then going to configure that project against the actual hardware that we've just pulled out from Vivado. So we're going to take the XSA, pull that into our PetaLinux project, and our PetaLinux project is going to configure around that implementation that we've just created. Once we've done that, we can also make changes if we want. So we can add in drivers into the kernel. We can add in applications into the root file system. We can, if we want, and we're going to create an application in this, but we're not going to build this into PetaLinux. We're going to build this in Vitis. But presuming once we've finally gone through this and you've finally got your application that you want, then what you can do is you can take that C file, that C++ file, and you can build it in to your PetaLinux application such that it deploys with your PetaLinux application because it's built into the file system. And then people can use it. And of course, it's going to give us everything we need to create the boot images for the file and to help us boot the board and work with the board. And we'll be able to see my little one over there in a little while. It's up and running, but we'll put everything new on it again, and we'll work through it and show just exactly how that can work. It doesn't take a huge amount of time to get up and running and doing this. So if you're not familiar with Yocto, this is one of the key elements, and it's one of the nice areas where industry came together, shall we say, to collaborate to create a better project. You know, it allows everybody to use their own distributions, but it has like a standard build process to it. So when you change from one target to the next, you don't really have to go away and learn about how to get everything building. The build tool is called BitBake, and the elements that we create in there are called recipes. And those recipes will tell us how to create applications, or how to add in new layers and new drivers and such like. PetaLinux just wraps around the Yocto. So if you want to use Yocto to build PetaLinux, you can. I think there are some links on my site showing you how to do that. But basically, when we call petalinux.build, as you will see, what's going to happen is it's going to call under the hood, it's going to call BitBake, and it's going to build us the application using BitBake, which is really quite important. This is one of those. Yeah, we'll put all those on at once. So, I mean, Yocto is quite nice, you know, because it means that we don't have to learn a new design tool every time we want to come across it and use it. So it gives us a lot of benefit, I think, in that respect. So I'm quite keen on it, and we've used it for both the using PetaLinux and just using the sort of the bare Yocto flow. One of the key things about Yocto, and I have to mention this because we're going to see it when we talk about it with the MicroBlaze in a little while when we start working with it, is it has a number of layers. And these layers are really important because when we work with PetaLinux, there's only some layers that we can make changes to. And if we make changes in other places where we're not, where we shouldn't do, then even though we think we're making a change, it'll just get overwritten by the automatic generation. So we have to think about the layers that we can use. So you'll see it's kind of a very specific layer approach that they have, where they have the actual core at the lowest level, then Yocto, then the BSP, then the user interface, then commercial, then developers layers. In our AMD approach, in our MicroBlaze approach, we'll see layers such as MetaXilinx tools, we'll see a meta user layer. Now that meta user layer is about the only place we can make changes unless we've added in new layers into our design. And we'll see that very shortly once we get into the embedded Linux solution and we start working with that. But that's the really important area. This is the really kind of the key message to take away from this slide, is the meta user area is really the area that we can work in and we can change elements in as we go through and we want. When we look at the structure of the PetaLinux project that we're going to get, once you've installed the tools, you'll see the tools installed in the green area like above. So you'll see the all of the necessary things. When we create a project, again, you'll see the structure that's shown in blue there. So you'll see the project, you'll see the components and the PetaLinux workspace area. That's going to be auto-populated and auto-generated. You'll see the images area. So this is where at the end of the process, end of the build process, this is where you'll go to find the images that you put onto your board. Obviously, the build area is where it's going to build the files, but the project specification area is where we're going to see elements such as the configurations for the root file system and the kernel and U-boot settings. We'll see the hardware descriptions. We'll see the meta PetaLinux generated area, and then importantly, we'll see this meta user area. And this is the area that we can work in and we can change. So under there, we'll see any configurations that we've made. We'll see any recipe changes that we've made for applications, any changes that we've made to the board support package, particularly the device tree that we want to work with as well as we go through it. So this should give us a nice, this gives us a nice flexible environment to work in and to create our PetaLinux solution. Not going to spend a huge amount of time on this, but this is the key area that we will see. The meta user areas that we will see. For example, there are recipes for the kernels if we need to do any kernel patching, or any modules if we create any modules. By and large, the area we spend most of our time in is the recipes and the recipes for the apps and the recipes for the board support package. One element of this that we're going to play with today, so I'm just going to talk about it a little bit, is the device tree source and the device tree. So the device tree source is a textual description of the device tree, and that device tree is going to basically tell the kernel what's connected to its buses, what nodes it's got, what drivers are compatible with it, and therefore what to load as it boots. And this is a really good thing for embedded Linux, because it means that embedded Linux doesn't have to be recompiled every time we change the hardware configuration. We can just change the device tree. The source is what we edit, and as you'll see when we get to it later on, and I will show you in a little while, there will be multiple sources for a PetaLinux project. And only one of them, or multiple ones, if we decide to create it, can we edit and change and will have any effect. If we change any of the other ones that are automatically generated, then they will be lost. What's actually used in deployment and packaged up is the device tree blob, which is a compiled version of what we've got in the source, as you would expect. And then we have the device tree compiler, and it's the device tree compiler that is running through and is compiling that source into blob, but it will also do the blob back into source if you happen to just have a blob and you've misplaced your source. So that's really quite nice and important to help us do that and work through it. Taking a look at the structure that we have in the device tree, and you will see this as we go through and we get into the lab. What we're saying here is we're pulling through, for example, the AXI I2C interface that is located within the programmable logic. We're saying that this is compatible with the Xilinx I2C driver library, and actually we're telling it, because this is a simple device, we're telling it what it's compatible with and what the library is, so it can go away and it can load that in. So for Cylin, this is actually generated by PetaLinux as we go through it. But actually, this file, this little bit of a file where we add in this little bit of information, we have to do this by hand, but AMD have a lot of guidance and show you how to work with it. If you think about it, it's a very simple thing. So if we put hardware in the programmable logic, then Vivado knows about it, and it can be put in the XSA, and it can be taken through and pulled through into PetaLinux, and PetaLinux knows about it, so it knows what drivers to pull through and to mount. If we have things on the board that are connected to the FPGA, be either on the MIO pins or the PL pins, it doesn't have any understanding of it. We understand it because we drew the schematics, so we've got access to the schematics, but we don't know what's available. So we know what's available, but PetaLinux and Vivado don't. So we have to add that little bit of information if we want to particularly say, you know, this has actually you've actually got a driver for this device that's connected to your I2C. Hopefully that makes sense to everybody. Like I say, this is all going to be created for us automatically as we go through PetaLinux and the creation of it. And all we're going to have to do is make some minor edits at the end. Yes, Brian, it is. After we've exported the XSA and we pull it into PetaLinux, we can create all this and get this all up and going. One last thing, once we've done this and we've created all this and we've got it all ready and we've got our project ready, there's going to be a lot of configurations that we put in there. So we're going to have configured the device tree, we're going to have configured the board, so we're going to configure the kernel and the root file system with the drivers that we want, and we might want to use that same hardware and that same application, that same setting for PetaLinux again on other projects or other variations and things like that. So what we can actually do is we can create what's called a PetaLinux board support package, and we can package that, and then we can use that board support package to create new PetaLinux projects in the future. And when we do that, instead of creating against the empty template like we did previously, that we then had to pull the XSA in and we had to set up all of the file systems and kernel, we can then just use this BSP and voila, everything just comes to life, configured exactly as we want for that target board. So if you're considering to do a lot of work with embedded systems and with PetaLinux, then that's the best thing to do. When it comes to working with this, we're going to need to have the memory management unit turned on and put in there into PetaLinux, because obviously Linux doesn't allow the use of physical addresses. You know, everything that's on the system, it thinks that it is the only application running, and it gets a virtualized address. So we're going to be using the memory management unit within the MicroBlaze configuration. That allows every program to to believe it's the only one on the CPU, and each user program, it's going to get its own unique, very unique address space. If we want to, though, we can punch through this. There are tools like devmem, which will allow us to just jump through and punch through that. But we have to be very careful, very, very, very careful with this. So let's be careful with that and try and use sensible things such as UIO and such like to do that interaction with the peripherals, because that's what it's intended to do. We've talked about this a little bit already. The PetaLinux, the BitBake, and the Yocto, and it's just PetaLinux wrapped around the Yocto flow. So we'll not focus too much on that. The last thing I want to talk about is really what's in these BitBake recipes, if we see them, if we want to create them for our applications. And we'll see that what we see is a description of the package, the location of the source file, the source code, and that source code could be located either on our file system or in our build machine, or it could be located in a GitHub repo somewhere that we want to pull down and build. We then give it the instructions as to what we want to do with it. Where do we want to put this? How do we want to make and compile this? Where does it want to be installed? How do we do the compilation? And how do we do the installation? And this is just a really simple overview. But if you get to the stage where you want to then start creating applications, the BitBake recipe to pull this in is actually quite important. So what we're going to do now is we're going to take a look at the lab, and we're going to start running the lab. So I'm actually going to minimize that and have the instructions on my screen. And then over here, I'm going to open open Vivado. And we're going to get started with the build, and we're going to start creating our project. So we've got about an hour and a half just to create this project. So we're going to start a new project in Vivado. I'm going to call this one MB Linux Live. I've already run through this several times, so we've already got a created one. What we're going to do is we're going to click on next for that, and we're going to say it's an RTL project. And that we're not going to specify the sources at this time. Now, when it comes to the boards, I am going to pick a board that is that I've got available to me, and you can all pick the same. I'm going to pick a Digilant one, and I'm going to pick the RTA35 because that's the one I happen to have in the lab when I built this course. If you've got a different one, as long as it's an FPGA based one, not a SOC based one with some DDR and an Ethernet connected to it, you should be able to follow along, and it will make sense to you, and you should be able to do it. It's a little bit more tricky if you've got a a SOC based one, because we need to be able to easily access that DDR for running the application from. So I'm going to click on next for this, and then I'm going to click on finish, and this will create me a new project. Once we've done that, this is our environment that we can see for Vivado. So we can see the device that we're targeting, the language that we're using. So I prefer to use VHDL rather than Verilog. We can see the board that we're targeting, and some information on the board. We're going to come down here and we're going to click on create block design, and we're going to use IP integrator to help us do this and to create the application. So let's click on create block design. And now, since I got told off the other week for just always using the name design one by somebody when I shared a blog on LinkedIn, they're like, I hate you doing this. So we're going to put a name in for this. And we're going to call this one, I can't remember what we're going to call this one. We're going to call this one MB PetaLinux. So MicroBlaze Petalinux. It was you, Howard. You see, I do listen and make sure that we do it properly. It's a horrible habit of mine. So we're going to call that MB PetaLinux. We're going to click OK, and then it's going to take a few seconds. It always takes a few seconds when my computer's both doing something and sharing a screen, and then it's going to create a block diagram. I think, Jonathan, it's not very descriptive, so it's not a good thing to do. Typically, I don't do it on my customer projects, but I'd fallen into a habit of doing it quickly on the blog. So I'm now trying to avoid doing that. Once we've got this is going to open us up with our IP integrator block diagram. What we can do is I'm going to go click on the board tab, because this is aware. So because we've said we're using an RTA35 board, the tool is familiar with the interfaces and the connectivity with it. Yeah, that's a good point, Howard. It is like calling your FSM states S1, 2, and 3. Once, many years ago, for a joke, I wrote one where they were all named after Star Wars characters, and it got very confusing if you're in this state and you went from Darth Vader to Princess Leia to Luke Skywalker. But what we're going to do is we're going to drag this system clock element onto the block diagram. And then once we've got it on the block diagram, we're going to click OK. Now, what we need to do is we need to make some changes to it. So once we've dragged that on, we're going to drag on our DDR3. So we're going to pull across DDR3. Brian, so Qemu will work to simulate the MicroBlaze Petalinux. It doesn't have to have the sort of the arty personality with it. So it should work okay. So I'm going to pull the DDR3 memory across as well and drop that onto the board. And we're going to click on OK there as well. Now, once we've done this, what I'm going to do is I'm going to double click on this clock wizard, and I'm going to change some of the clocks. And of course, like everything else, it never quite fits on the screen. So we'll make it a little smaller there. I will make it a little smaller there. And then I'm going to click on output clocks. I'm going to enable 3 clocks for this. And then I'm going to give them some names, actually. I'm going to call this one clock out 100. I want 100 megahertz clock out. I want a 200 megahertz clock out. And I want a 25 megahertz clock out. And then I'm going to change this to 200. We're going to change this to 25. And then we're going to scroll down the bottom. I'm going to turn the reset off because I don't want the reset on it. And I'm going to click OK. Once we've done that, we can see that we've now got the outputs 100, 200, 25 on here. I'm going to delete this clock reference here and get rid of those two because I don't need to use them. I'm then going to connect this up, and hopefully I can remember how to connect this up properly, because I always get the ref clock and the system clock the wrong way around on this. But the ref clock should be come on, start drawing me a wire. What's going off here? Start connection mode. What's going off here? Let me just move this over onto a different screen for a second so as I can see. Why doesn't it want? To go from one connection to the other. This is very odd. A little oddity, this. Yeah, the ref clock should be 200 meg. For some reason. Why won't it draw? What am I missing? Come on. What's going off here? This should just add a line from one to the next. That'll move okay there. Yeah, I'm not doing, let me just see if it's something on my different screen. Otherwise I might have to open it, and let's just save it, and then I'll open it and close it again. But it doesn't seem to want to draw. I'm going to add another IP block on here. Let's just try a logic utilities one or something and just see if we can get that to do it. Ah, yes. Okay, that wants to play now. So does that want to play? Aha! Look at that. Sorry about that, everybody. It's some weird mode in Vivado. I added in a new block, and it sort of it worked okay, but it didn't want to do that. So the ref clock is 200, the system clock is 100, and we're going to make this one external. I think I've connected those the wrong way around. Yes, I have. The sys clock is 200, the ref clock is 100, and then we've got the external one going out there like that. That was really weird. I've seen this view do a few times, and I've never seen it do that. We'll get it working live, Jonathan. It's always I've done this quite a few times before, and it's always kind of worked okay. So what we're going to do now is we're going to go over to the MIG option, and I have like in the Best Blue Peter tradition, I have actually got all this pre-built as well, just in case it goes horrendously wrong. We're going to click in on next and next and next. We're going to click on next again, next again, next again. And then on the system clock here, we're going to change this to no buffer. Next again, next again, next again. Validate that. That'll be okay. Oh, it better be okay because it's not mine. We're going to click on next. We're going to click on next. We're going to click on accept. And we're just going to finish this process. Once we've done this, we can start thinking about building our MicroBlaze, which is what we're all here for. I was still puzzled by that error. That was really really odd. So we're going to add in a MicroBlaze. So we're going to double click on MicroBlaze here. And then we're going to run the block automation. And in this block automation, let's see if I can get the presets right and remember the presets. So we're going to have a preset for the application. We're going to set the local memory to 32 kilobytes. We're going to leave that as debug only. We're going to have the AXI port enabled, the interrupt controller port enabled. We're not going to have any local memory ECC, and we're going to click on OK. And technically, we probably don't need the debug port because I don't actually plan on doing any bare metal development on this, but it's useful to have it because sometimes if you get some of the resets wrong or the clocks wrong or something, then your processor gets held in reset and you'll not see it when it's running with PetaLinux. So it's much better to try and include that just so you can do a quick bare metal debug if there are some issues or questions related with that. By the end of this then, so let's just move this across here a little bit. What we'll see now is we'll see the MicroBlaze. We've got the local memory connected to it. We're not going to really run much of our application from that. We've got the system reset controller. We've begun to get an AXI interconnect system, and we've got a interrupt controller all set up in there, just like we would. What we want to do though, we're still not quite there with the MicroBlaze, so we need to double click on this. And then on page 7. So yeah, someone was just asking if it's all recorded. So yeah, I will share it. It will be, you can use the link you've got. So it will bring you back here to see it. I'm also going to put it on my YouTube channel and with a link from my website, so as you can see that. We're going to enable the peripheral bus as well. And once we've done that, we're going to click OK. And then we're going to run the connection automation. I do like this about Vivado. It really does a lot of the heavy lifting for us. And we're going to collect all of these according to my instructions here. We're not going to make any changes, and we're going to click OK. And this should run through. And at this point, I'm going to pop this out a little bit just so as we can see it and see it a little bit bigger. I'll pull it across the screen here. Oh, doesn't like doing that. Where's it gone? I'll restore that actually. Keeps jumping about onto different screens. That's a good question, Sirif. I always just selected the application one. It should be okay. Should be okay for that. And that should pull through actually and include the MMU. Let's just double click on that and see. We go from the application one. Oh, that's because the reason I selected it is because there's only a few options available initially, I believe. So now we have to do something with the locked signal. So let's just zoom in. So the locked signal is going to the DCM locked of the wizard. We're going to put it into the system reset of the MIG7 here. Look at that, the connectivity thing still works. And then on our next one, because we want to be able to have a terminal or something, so we're going to come back over here to the board tab. We're going to grab the USB UART, and we're going to drag that across and throw that on there and add the USB UART. I think we're going to add a couple of other things on at this point in time as well. We're going to add on the Ethernet, because obviously the only way we can work and debug a Linux application is by having Ethernet. So we're going to drag across the Ethernet MIII. And if anybody's curious, that's what the other 25 meg clock is for. So that's to provide a reference to the PHY on the board. So the role of the MIG, this is a good question. So the MIG is the memory interface generator. So on this board, we have DDR3. I can't hold up the board, it's over the other side of the room. But on this board, if you take a look at it, we have DDR3. Now, an embedded Linux application is actually quite large. So there's no way we could run it from the internal resources of the FPGA in terms of block RAM or such like. So we have to use an external memory such as DDR. The memory interface generator, it does all of we basically tell it the device that we want to talk to, the memory type that we want to talk to. So DDR3, DDR2, DDR4, LPDDR4, depending upon the device that we're working with. And that will create an interface that enables us to talk to it over AXI, and it will do all of the configuration, the control, the timings to actually read and write from that external device, hence the name, the memory interface generator. And it's going to be in the MIG that we're going to be putting all of our applications, all our operating systems, as you see when we come to download it and run with it. So we've added that. Then we're going to add in a quad SPI. Oh, can't type. So we're going to add in the AXI quad SPI. We're adding in a lot of IP. We're adding in a lot of IP here. We also need to add in a timer for embedded Linux to work. So we're going to add in the AXI timer. Notice I'm not actually doing the auto mapping or anything like that. We'll wait till the end of that. I think the main thing, I'll run through this again, Brian, because I'm curious about that question as well. I think the main thing is when you first do the block automation, I think the only thing you've got is to be able to select the app, is either to be able to select a bare metal, a real time, or an application processor. And I think that's the reason why I selected it, not the Linux MMU. But we'll double check that in a few minutes at the end of this session. So we've added in the AXI timer. Now we've got a few things in here. So we're going to run the block automation, or the connection automation. I'm not going to connect any I/O up for the moment. So I just want to connect my AXI networks. So I'm going to connect my AXI networks just like that and click OK. I'm going to give it a second to run through. And then I'm going to regenerate my layout just so as we can see it. What we should see then is we've got a number of things down the output. So our timer, our UART, our SPI, our Ethernet, and our MIG. What we want to do, though, is because this is a Linux-based system and Linux works off interrupts, and we've already got this set up for interrupts. To regenerate the layout, there are these two buttons up the top. So this one will actually do the entirety of the layout, and this one will just tidy up the routing a little bit for you. Now, because we've got this, we've got a number of systems that want to be connected to our concatenation, to our interrupt. So we need to connect the interrupts up. So what we're going to do is we're going to double click on the concatenate block, and we're going to say that we want 4 inputs. It's very confusing. I keep looking at you and looking at my Vivado screen and seeing the Vivado screen on here and thinking I'm editing it in, trying to edit it in that. So we've that's a good question, Brian, because this is actually, if I pull this across the SPI flash, it will connect it and it will come through and it'll have all of the connections and the board connections to connect to the flash device. But actually, I don't want to connect to the flash device in this. I actually want to connect the AXI SPI to a PMOD location. So that's the reason. why I'm doing that. And the AXI protocol, yeah, it does come from the ARM processor, you know, from the Amber thing. But actually, it just makes everybody's life a lot easier if you use the AXI interfaces. And MicroBlaze was redone many years ago to have the AXI interfaces. And I'm quite excited. I don't know about you all, because I'm really sad and I'm an FPGA engineer, but I'm actually quite excited to have the RISC-V MicroBlaze coming out soon. So I know there's going to be a number of releases of it, and that's going to be quite cool. So Giacomo, yeah, it is possible to have it running, not to run PetaLinux from the SRAM because it's just too big. So you have to run it really from the DDR, because there's not that much. There's not sufficient memory really in the in the FPGA to be able to run the Linux system from it. I'd love it if there was. Maybe you could get away with it on something like a Versal or something. Maybe I'll take a look at it on that and see what there is. What we're going to do then is we're going to hope the connections are working correctly. And what we're going to do is we're going to connect each of these interrupts back to one port on this concatenation block. So the timer, the Ethernet line, the interrupt, and the interrupt from the QSPI. Jason, yeah, you could do it in an external SRAM, provided it was the right size, because to be honest, it's just talking over an AXI interface. It gives me a good thought for another project, not something. Sorry, Giacomo, I misunderstood that question. I'm multitasking, but yes, you potentially could. The Digilent A7C mod has an SRAM on it. Exactly what I was, and I've got one, and I need to play with that. So I'm curious if now you've got me thinking if I can get that running using PetaLinux. So I don't know, but if you're trying, I'd love to know. What we're going to do then is we're going to come over to the QSPI. I'm going to double click on the QSPI here. That's going to give me another configuration window. What I'm going to do is I'm going to change its transaction width to 32. I'm going to disable the startup primitive because I don't want to access any of the startup elements. And I'm going to leave everything else as it is and click OK. And then I'm going to go through and we're going to zoom into this because I don't want to break out all of the pins. So we're going to zoom in to this area down here. I'm going to expand this. And on this one here, so the output here, I'm going to make this external. And for that pin name, I'm going to give it the name master out slave in. So MOSI. We're going to find the S clock out, which is this pin, and we're going to make that external. And we're going to call that one S clock. Just reminds me now whether I've uploaded the XDC file to the drive that you've got available. Maybe not. I'll make sure I do this straight after. We're going to go to the slave select output. We're going to select that one, select that pin, and we're going to make that external as well. And I'm going to just call that one slave select. I'm going to also add in a constant block. And I'm going to connect this constant block to this slave select, still in routing mode. I'm going to add it to this pin here, just to make sure that that it never accidentally thinks it's acting as a slave mode. Don't know if you actually need to do that or not, but it's something that I've always done. And then once we've got that, we don't need an input because we're not reading anything back. So we don't need a slave out master in. So our design should look like this. We'll regenerate it a little bit, tidy it up a little bit there. and our design should look like that. What we need to do though is we do need to connect that external SPI clock to the other clock that's connects to it. Hopefully I did that right. Those two clocks connected together, yeah. Okay, so now we end up with at about the hour mark. Oh, this has taken me a little bit longer than I thought. We end up with a nice Vivado system that's going to give us that's going to run and generate and give us a nice MicroBlaze solution. All we've got to do then is we've got to where's my mouse gone? We've got to come over to the source tab. We've got to click on the source tab. We've got to actually create a HDL wrapper. And that's what we're going to do. We're going to let Vivado manage that as we create the HDL wrapper. Now, in a minute, I'm going to switch projects to one that was well, that's okay. We can click OK on that. And that's not going to be a problem. So now we're in a position that we can synthesize our design and get this up and running and start working with it. However, what we've not done, and there's another thing I've not done. Oh, we've got all the pins external. There are some pins that need to have constraints on them. So the board's really good because this is board aware. It knows, for example, where the pins are for the DDR, as you saw. It knows where the pins are for the Ethernet Lite as well, and it knows where the pins are for the USB because the board, all that information is contained in the files that DigiLink gave Vivado to tell it where the board is. Unfortunately, it doesn't know where to put our clock 25 out, and it doesn't know where to put our MOSE, our MISA, our MOSE, our clock, and our slave select line. So we have to do that by creating some constraints files. The normal way, you can write the XDC to do that, but you can also run the synthesis and then go into open the synthesis view and do that. So I'm just going to quickly open the project that I ran this through earlier on because I'm presuming nobody wants to sit and wait for half an hour while this synthesizes. So I will just close this project momentarily. And open it. The reset pin is just going to get tied off, and it's because it's an FPGA, because it's a SRAM based FPGA. It shouldn't cause any issues in the design. I'm going to double check this in the MicroBlaze one that we're about to open to make sure that I've done the same thing in both of them, but it should be okay. So the reason I'm switching projects just to one that's previous. Oh, this one's not been. Yeah, this one's implemented, is that we can show it. And if I open this again, just to show you that it's the same, just show you this same thing. This is the, oh, maybe I did tie off the reset pin on this one then. External reset in. External reset in. Ah, yes, I tied it off to a constant. So sorry, you're right, Brian. I must have missed a step in the instructions, but I tied this off to a constant 1 to prevent it being in this one. What we can do though in here is we can this is running on the bench, so I'm not going to run through and worry too much about those timing violations, and I know that, and you wouldn't do that for production. But it should be okay. It should be okay for this. Just don't run it at temperature. But it's sat running behind on the bench. And they're only very minor timing violations. So we'll open the netlist, and then I can just show you where the pin is. So that's a good question. Between the global and the out of context simulation, while this opens, we'll just talk about that. So in a global yeah, that's a good point actually about the MIG. In a global synthesis, we have all of our files, and the synthesis tool does the standard sort of thing. It does the top-down synthesis, synthesizes them all as it needs to, optimizes across boundaries, etc., and then gives you a nice file out of it, a synthesized netlist out of it. The difference is if we change one element to that, say we get something wrong. I know that's unusual that we get something wrong, but you need to change an element in it. what will happen then is the entire thing has to be resynthesized. By doing the out of context synthesis, what happens is every module is synthesized on its own. And then at the end of that synthesis, it then takes those modules and it does the full overall synthesis, pulling in the synthesis results from the pre-synthesized modules. What that means is if we change a little module somewhere, we don't have to resynthesize everything and things that might take a long time to do. We just have to resynthesize the module that changed and the overall top module. So just to look in this view here now, this is the I/O placement view, so we can then see that all of the pins are locked and placed. And for the MDIO, we can see they're locked and placed. We have some elements here for example, we've locked we've put the slave select and the SPI, tied those off to package pins as well. And somewhere in here, there should be a clock 25. So we've assigned the clock 25 as well. This will get written to a file called a XDC constraints file. So we can see this here. This is the one file, actually, I don't think I've put on the GitHub repo yet, if you want to follow through and do this. So I immediately after this, I will put this on so as you've got it and you can take a look at it. And see it in its full splendor. Once we've got that, though, we just need to place and route the design and run through the design. So yes, so there's an interesting point about DDR controller interface. Why not use the AXI DMA? You still need to have some physical something implemented that implements the protocol and the DDR that the DDR uses. So in our system, for example, if I just close this design here, if I wanted to do DMA into and out of the MIG, where is the MIG? So the MIG's here, into and out of the MIG. I would have to connect the DDR, the AXI DDR in front of the MIG, because by and large, the AXI DDR, the AXI DMA doesn't know how to interface with the physical memory chip that's external to the FPGA. Only the MIG knows how to do that. So I hope that makes sense. Once we've done this and we've run it through, you'll see the right bit stream complete in the top corner. And then we can go through and we can do project. We can go down here, so we can go to export hardware, and then we can roll this through. Obviously, we want to include the bit stream in this at this point in time. So we're going to include the bit stream. We click on next. We're going to tell it the location to export it to. We click on next. It's going to say, hey, there's one already existing. Do you want to overwrite it? Yes. And then we can click on finish. And then we have our XSA that we can pull into PetaLinux. So now we're in a position that we can start working with PetaLinux. So I'm going to minimize this for the time being. And I'm going to pull across and I'm going to open my remote desktop machine here. In fact, I'm going to momentarily stop sharing this screen and actually just share the remote desktop connection so that you can probably see that a little better. So if I remove that stream there, kill that, confirm, then I'm going to share screen. I can probably share a window, probably share this window here. Is that better for better for everybody to view, I guess, than it was previously. Makes it a little bit better. I'm going to pull this across onto a different screen so that I can actually see it, because on my laptop screen, I'll be honest with you, I couldn't see it at all. And what we're going to do is we're going to come over here and I'm going to close this down for the time being. I'm going to, where are we? So the first thing we need to do, and I'm going to do this in that's a terminal. So I'm going to minimize that terminal and I'm going to minimize that and that. And I'm going to minimize that one. So the first thing we're going to do is I'm going to open a new terminal. And in this new terminal, I'm going to tell it I'm going to source the PetaLinux installation so that it can run PetaLinux. If you look at my home, just to show you, you know, I've got various different versions of PetaLinux installed on my machine. So I need to tell it which version and which flavor I want to use. Obviously, I'm going to use this one today. So I'm going to say source PetaLinux 23.2 settings.sh, and that's just going to mean that I can then pull through all of the commands. I'm going to change directory then into where I like to keep my PetaLinux projects, just so that I can see that I've got it, keep it in the right place. Once I've got that, I'm going to create a project. I'm going to use the command petalinux-create. I'm going to tell it that it's a type --type, that it's a project type, and I'm going to this is going to boot from the initially we're going to show this from JTAG, but we're not going to. But you can use TFTP as well to boot over the network if you want. It's a project. I'm going to tell it that the template processor that it's being created for is the MicroBlaze. And then I'm going to give it a name, and I'm going to call this I'm going to call this MB Live. It's going to create me a PetaLinux project. I'm going to make this a little bit wider actually, so as I can come on. So as we can see some stuff. I'll call this PetaLinux Live, and then I'm going to go find my I'm going to CD into that project. So I'm going to CD into ls CD MB Live. So I'm going to change directory into that project Live, and if I do an ls again underneath it, we'll see at this time it's just the project spec. There's nothing there. There's just a very basic template of a project. Now under my PetaLinux project somewhere, I'm going to go under here, and I copied across the this is the PetaLinux XSA that we exported. You'll have to take my word for it, but Scout's honor, it is. I'm going to put it under my MB Live project just so as we can see it. And then I'm going to run a command to do the PetaLinux config, PetaLinux-config. And what this is saying is you can have this file anywhere in your file system and get it, but actually in this case, I just want to get to it using the using it simply, which is why I just put it one level above. And get hardware description equals ... Let me just check I've spelled that right, because I always spell that wrong. Get hardware description PetaLinux config. Okay. It then finds, as you see, it then finds the XSA that we've got above, and it's going to start creating the PetaLinux project in more detail for us. So this is going to give us now the configuration for it. So we can see that we have the MicroBlaze configuration. We have the configuration for the setup there. We have the auto configuration. That's actually picked up the wrong file because I typed in something wrong in there. So no, I don't want to do that. So I'm going to go and pick up the project that I had open already, having created it with the PetaLinux project, just so that we're all on the same page and have that. So it is this one. So once you've done that PetaLinux create, yeah, I should have put it I put it in the right folder. I put it in the wrong folder. But to save go deleting everything and do it, I need to switch over to the project I've pre-built anyway, because it downloads everything from the web. So what I'm going to do is I'm just going to call and show you what it is, PetaLinux config. And this will come through, and hopefully this will show us the right thing now. So we've got the hardware processor MicroBlaze 0. We can see where the address is. Apologies about that, everybody. You know, when you do things live, sometimes it's a bit difficult to keep your head on a swivel and work out where you're going and what you're doing. You'll see that we've got the settings for the AXI UART Lite for our system. You'll see we've got the Ethernet settings with a MAC address in there. We have the flash settings, although we don't have anything in there at the moment. And we've got the processor, obviously. We can change anything that we want in terms of how we want to do image packing. So whether we want to have a RAM disk or whether we want to have a disk on a non-volatile memory somewhere. I'm going to keep this as a RAM disk for this point in time, and then we'll take it from there. There are some other elements in there that you can change. Don't ever change the host name or the project name. It tends to not work. Yeah, Fahad, you can use eMMC instead of SPI flash. You can use an SD. That's a good question. You can use eMMC provided you've got a driver for eMMC, because you'd need to create the interface in your programmable logic to do that. If you're using a Zinc or MPSoC or a Versal, then yes, sure, you can do that. With the MicroBlaze, it's a little bit more constrained. So we're going to run through that, and we can see that then that's created our project, and we should be good to go at the base level for this then. We don't need to make any changes to that, but what we want to do is we might want to configure the kernel. So if we want to just configure the kernel elements of it, we can do PetaLinux config -C and tell it the element we want to configure, which in this case is the kernel. Now this is normally where it will take a while to download, but hopefully I've actually got all this downloaded and built, so it should be able to build it from the cache. He says hopefully. So if you've got any questions, please just throw them in the chat. Keep asking them as we go through. What we're going to do in the kernel is we're going to make sure that we have the SPI drivers that we need enabled, so as that we can use the user mode SPI drivers in there. That's all we want. That's all we want actually from the kernel, just to make sure that we've got that all set up and do it. I don't know, Tobias, if anybody's ever tried to do it from WSL or WSL2. In theory, it should be possible. It should be relatively simple. It should be possible to do, but I don't know if anybody has. I'll take a look around and I'll see if I can find some time to create a blog on that. Making a note now. And then we'll see here what we see. We see here the standard sort of the MicroBlaze configurations and all of the libraries that we're going to do. So Jonathan, you were saying, so we're loading the Linux image and whatnot via SPI to the DDR and not creating something that booting from non-volatile memory because it's too large to fit on the SPI. No, this should be fairly small. This actual example is going to be fairly small, and it will actually fit on. It will actually fit in SPI, and it will boot from the SPI memory. For this example today, for downloading and debugging, I'm just going to show you how to download it over JTAG, purely in the interests of time. But yeah, these small images will fit on a small on a SPI, particularly because we're having it relatively small there. So what we want to do is in this element here where we've got the Linux configuration, I need to go down. We need to scroll down until we see device drivers. We're going to hit enter on device drivers, and then we're going to scroll down until we see SPI. Somewhere down here, I2C, SPI, we're going to hit enter on SPI. And then down here somewhere, we're going to pick up the user mode SPI. So the Xilinx one's already configured because it can see it's already configured. And we're going to pick up this one here, which is user mode for SPI devices. So this means that we can use SPI dev in our application to get access and control of it. So we're going to click on that. We don't need to make any more changes to the driver, I think. So we're going to exit that if it's not already saved, and we're going to exit that, and it's going to take a few seconds. So the thing is, this is giving you the entirety of the, it gives you the entirety of what's in there for SPI and for all the different flavors of Linux, because Linux supports lots of different things. So by default, the Xilinx ones are in, when you load that XSA in, it enables the one that you need. The user mode ones are there because I knew that there was a thing called SPI dev that I wanted to use, and it's not enabled by default. And then I Googled and looked at Windows, and it said, hey, you need to enable these user elements in the file there. So there's some good points coming up about looking at the the other Vivado IX IP. So it generally will pick up other IP. So if you put in like any AXI related stuff, DMAs, it will generally pick it up, and then you can work with it using UIO. And at the end of this, I'm not going to switch and show it now, but at the end of this, I can show you some blogs, some links to some blogs that I've written on my blog, where it shows you how to do that using UIO, and how to work with these peripherals, and how to how to pick up interrupts and such like from the from the user space, even though in the kernel space using UIO. So it makes it nice and simple. The key thing here then, coming back to this project, is we want to go under here, and we want to go under the project spec, and under meta user, and under recipes BSP, and device tree, and files. And we need to make some changes to this device tree. So we need to basically tell it that the AXI quad SPI 0, so this is the name. This is the name that we had in our Vivado IP block diagram. So we need to tell it that we need to add this to the configuration. So we need to tell it that its status is okay, so it's being used. And then I want to tell it that actually I want to use SPI dev at select line 0, so slave select 0 SPI dev, and I need to tell it it's compatible. Now, when you say compatible is the driver to load in the kernel. Now, you used to be able to, in earlier versions of Vivado, there was a little bit of a issue, shall we say, a bug, feature is probably the right word, where you could say compatible SPI dev, and it would work, and it would pick up the SPI dev libraries. That's not strictly compatible with the sort of the Linux and the upstream Linux. So now you have to put in this if you want to use SPI dev, you have to put in the name of one of the devices that's supported by SPI dev, which happens to be this little Roam device. We're not going to use in any way, shape, or form this Roam device, but that's what the name is there, to get it to pick up the SPI dev libraries that we want to work with. Then we can do we can tell it what the maximum frequency is and the register. So it makes it nice and relatively nice and simple to do that. And that device tree thing will be put on the GitHub later on this evening, so as you can take a look at it, and it's in all of the slides. At this point, this is all we need to do. We're good. We're ready to go. All we need to do is run a PetaLinux build. So we can type in PetaLinux-build, hit enter, and it will start the build process. That build process, depending upon the machine that you've got, the time it will take, might take a little while to actually do that build. 20 minutes, 30 minutes, cup of tea time. It's a cup of tea time element to do. Does that make sense to everybody so far? I'm not going to click on the build because I've already got I've already built this through in the Best Blue Peter tradition. So if we go here, we will see, when we go back to the top, under images, under Linux, we will see I've already got the system.bit, which is the bit file that's been extracted, and the image and all of the and everything we need to work on the on the board. So what I'm going to do now is I'm going to come over and I'm going to boot this on my board. So this board's already up and working, and I'm going to show that to you because somewhere I've got a GTK terminal window open. So this is already running. It's sat over there. I like a big cup of tea, Jason. I've got a huge cup of tea. I'm going to quickly go and, well, I'm going to leave that there. But what I'm going to do is I'm going to reflash the FPGA and download the FPGA. So what I'm going to do here is I'm going to issue the command petalinux-boot. Oh, can't speak or type now. Petalinux boot. And this is where you could boot it into QEMU or anything like that if you got QEMU and you wanted to. But I'm going to tell you I want to do it over JTAG, and I want to do the FPGA. So now I'm saying go away, boot, and just program the FPGA. So when I do this, hopefully it's going to work. We'll see now if I come over to this terminal. Yeah, my terminal's now dead because I'm just reprogramming my FPGA. And that should have reprogrammed the FPGA. And because it's a MicroBlaze, it's blown everything away. What I'm going to do now is I'm going to come over here. Yes, so this step is loading the bitstream into the FPGA. And that bitstream, obviously, in this instance, is loaded in the MicroBlaze processor for the MicroBlaze processor to run. I'm then going to tell it I want to download the kernel and hit enter. And it's going to take a few seconds for it to do. And what you'll see is it starts running in the terminal. So give it a few minutes. It'll download. If you've got any questions to do that, then just throw them in the chat. I'll take a look at the chat now and try and answer them. So how does customers use your own custom light? Hang on, I don't need to wrap my own. No, Jonathan, you don't actually. You can access it because it's on the PL. And I'll link some blogs at the end. I'm not going to do it now because I need to open my web browser and everything, and I'm always a bit nervous of doing things when I'm online. But you can actually use a thing called UIO and write a simple device tree update actually to tell it what to do. And then you can access it and treat it as though it's your own peripheral and just read and write it using the Linux UIO elements. It used to, honestly, this used to daunt me a little bit, but actually it's not so daunting now. David, do you want to expand on that a little bit? You can set a cache folder to speed up the build. Yeah, oh yeah. So there is a cache folder already built in for the build as well, so it should run through. And this will run through and build quickly now. I don't want to do it. I didn't want to do it because it's on my machine. But the fact is, if you do it for the first time ever, it will take a little time to download and to boot. So what we can see here then is that we can see now it's now starting to run through. We've now got the PetaLinux stuff up and running. Jason, DevMem will work fine, but if you remember back to my talking in the slides initially when I was talking earlier on about the what do you call it now? About the virtual memory and the memory management unit, the DevMem is kind of just punching a hole straight through that, so it can cause a little issue at times. So hopefully this is going to run through in a minute. This is connected to my network. And this is important that we need these things to be connected to our network so as we can grab it and start debugging with it. Oh, we're running. Yeah, we're running pretty well to time. We might finish a little bit early at this stage. Yeah, so you can still use UIO to do that. So if you've done like a DMA transfer into it, then you can pick that up and grab that data out of it relatively easily. Is everybody enjoying themselves so far? Is everybody learning? Is there anything that they thought I was going to talk about so far that we've not talked about? So I always have the Linux kernel. I just let it pull down the Xilinx kernel that Petalinux is set for. I don't go messing with the kernel. I'm an FPGA engineer. My job with Linux is to do simple things like this and to prove to the software team that it actually does work and it's their software that's that it's wrong. It's really quite powerful, I think, so far on this. Lib.io. I have some blogs. At the end of this, we'll go away and add some stuff in. And I've got a blog on lib.io because lib.io is quite useful. So I'll point you that lib to that. Vasily, the last Petalinux command, it actually uses JTAG over the USB to download the FPGA image, so that there's a processor in the FPGA, the MicroBlaze processor in the FPGA, and then it actually downloads the kernel and all of the boot system that's needed to actually boot the application. And what you can see now in this terminal window is the, of course, is it booting? It's just waiting on drop bear SSH. If I'd have thought on, I should have turned SSH off on this one or made it open SSH. But it will come up in a minute or two, hopefully, and we will have a terminal that we can talk to. And we need to know this term. The reason we need to see it boot is for the next element of the class. Which is where we need to connect and do some remote development with it, and that remote development we're going to use Vitis to connect remotely over the network to do it, and then that'll allow us to create an application and debug it. Now here's the interesting thing. Now we're going to have a log on. The username is always Petalinux. And then it's going to ask me to change the password. Now, remember, this has got a RAM-based file system. So I'm going to change the password. And then next time it power cycles round, it's going to ask me to change the password again because it's got it has no recollection because you can't change the RAM-based file system. This is Petalinux. And it's all doing, and it's now abstracted away from the hardware. It doesn't really matter about the hardware, whether it's a MicroBlaze, whether it's a Zinc MPESOC or Reversal. The principles are the same to interact with it, and that's one of the really nice things actually about Petalinux actually, and about embedded Linux. We have, just divert slightly, but we have this board I showed at the beginning. I'm just going to unconnect it so I can actually wave it about a bit. But we have this board that I was showing at the beginning. This one's got a Creo on it, so it's the K26. It's a custom carrier card that we designed. It's got an Ethernet on it, and it has the Ethernet clock is generated by a Skyworks. Would you believe a Skyworks chip? And I needed to program. You need to program the Skyworks chip to generate the reference clock for the Ethernet to come to life. And I was doing bring up with this. This is a new board. I'm trying to work out if it works or not. And I ordered it. I didn't realize this, so I ordered a Skyworks program. It didn't come for a few days, but I knew I could. I got Petalinux booting on it. And once I got Petalinux booting on it, I could put the I2C tools to it, and using the I2C tools, I could see the chip. I could see the Skyworks chip. And with seeing the Skyworks chip using a little bit of code simply in Vitis, I could write down the I2C sequence to configure the clocking chip such that it gave out the output. I could then see that spring to life, the Ethernet PHY and the LED started going and everything. So I'm like, that's good. It didn't quite pick up and work from Petalinux because it needed to be there from power on. But it gave me the ability to test it. But I guess my point here is using that flexibility, that ease of use of just kind of like, I just need to write I don't need to write a huge bare metal application to do this. I can just do this using Linux tools like I2C dev and just read and write the registers. So what we want to do now that we've got the terminal and it's still alive is I want to do ifconfig because I want to know what the address of this is. So it comes up on my internal network address. We can see there 10.10.30.13. That's good. That's actually the same address that it came up with earlier. And the other thing I want to check as well is that I have the SPI dev. So if you remember, we enabled the user SPI space, and that I made some changes to the device tree to do that. What I want to do is I want to make sure that that's actually reflected in the design, and I can see that in the design. So I'm going to look at the devices in here. So I'm going to do ls/dev, and then we're going to get a huge list of things, and then we're going to go looking for it. And you can see it there, scrolling up, SPI dev 0.0. So this is the device that we're going to work with to be able to control that AXV DAC that's on there. Does this make sense to everybody so far? Everybody's happy with this. We've got a Linux system running. It's running on our MicroBlaze. It's not the most performance system in the world, but it's pretty cool. Right? We've got a Linux running on a softcore MicroBlaze, and that's really cool. And it's really quite useful. What I'm going to do is I'm just going to stop sharing the screen again, and I'm going to flip back to Vitis. So do you have one differentially routed on that create carrier? Yeah, we'll come to that, Brian, in a minute. But actually, we do have some LVDS router. I'm going to stop sharing that screen again, just because now I want to open Vitis. So I'm going to close everything in Vitis, and I'm going to go to the welcome page. Actually, yeah, I'm going to close Vitis actually for the time being, and then I'm going to reopen it so as I can pick something, pick up the workspace to go through, and we'll go through it. Now I'm going to use 2023. I'm using 2023.2, obviously, but let me share my screen, share entire screen, share this screen, share. I'm actually going to use the classic version of Vitis, just because that's my preference. So I'm going to call this workspace live. It's in the, I have a thing, I always keep the workspace within the project that I've created if I'm doing stuff. So I'm going to launch this. This should open Vitis. And then it opens it on the wrong screen, of course. And then what we've got is we're going to create an application. We're going to create an application project in Vitis. So I'm going to come create project. I'm going to click on next. It's going to think a little while. It's not a built-in platform. It's not a built-in platform that we've created. So what we're going to do is we're going to click create from hardware XSA, and then we're going to browse here, and we're going to browse to where we created our project. So we're going to go see, it was Vivado project, and it was, in this case, it was MB Linux that's there, and the project is there, the XSA. Once we've got that, I'm going to click on next, and I'm going to give it a name. What we'll call it? Call it DAC Live or something. And you'll notice it's associated with the processor. I wouldn't do that to Howard, Jonathan. I don't know if he's still on. I don't know if he's still on the call, but I don't. That'd be cruel to do. It'd be funny, but it'd be cruel. So yeah, so we're going to have that on there, and we're going to click on next, and then we're going to be able to tell it what application we're creating for. Whether we want to create for a bare metal application, whether we want to create for a free RTOS application, but in this case, we want to create it for a Linux application. So I'm going to create for a Linux application. We did a 32-bit MicroBlaze, so I'm going to click on next. And then we get, I'd have thought we should have got a Hello World application coming up for that. Why don't we get a Hello World application coming up for that? What's going off there? We should get a Hello World, I think. Oh, well, we'll create the empty application for that. Bugger. Let's switch to the workspace that I know works. I don't know why that didn't work. FPGA tools, there's nothing like them. So we go there. This will come back. So we have our MicroBlaze processor here. Created the platform. We can then create an application targeting that platform. What was the reason it did that? There must have been a reason that it did that. Maybe it was in my instructions. Maybe it's because I didn't select. Oh, I know why. I know why it might have done that. So let's go back and try that again, actually, if everybody is okay with that. Yeah, it can be a little frustrating. I'm going to go back and try that again because I like to get things done properly. So I'm going to come here. I'm going to go here to my C drive. I'm going to find that directory. Not Windows. I'm not going to delete the Windows project. That'd be not Windows. That'd be silly. I'm going to delete the workspace live, and then I'm going to open the Vivado one again. Vivado Vitis Classic again. Get the IDE launcher. I'm going to tell it that I want to call it live. Click on launch. Certainly very brave people that do this live, you know. So we're going to click create application. We're going to do next again. I did one. I can't remember. I think it was with somebody on YouTube, a YouTuber, and I actually did it like built a MicroBlaze that worked in like 2 hours, and and nobody was more surprised than me that we'd gone through all the steps and it actually worked. Because I was like sat there all day thinking, what am I going to say when it doesn't work? But it is good. It is good fun. So we're going to go to the MicroBlaze Linux here. We're going to select this XSA again. We're going to click OK. I'm pretty sure I did something wrong here. No. Oh. We create the platform project. This is the reason. This is the reason we create the platform project. So we do MB live. Funny, I have more issues with the new version than I do with the classic, which is interesting as well. Yeah, no, it's just me getting confused today. It's me getting confused. We do this, we do this. This is what we needed to do. Linux, MicroBlaze, finish. And then onto this. Now we've got the platform live. For some reason, it can't create the platform and the MicroBlaze at the same times. Yeah, Jonathan, I do use the new version, and I'm just doing some training for Avnet on the Versal, and that's all in the new version. But I'm kind of I was just kind of clinging on to this as long as I could, really, to be honest. Cancel. No, we don't want to do that. We want to do file, new application project. Where isn't my hardware shown in that list? Should do this. Well, should do this. File, new. We've got a platform project, new application project. Next. This makes no sense. I'm going to switch to the other one because otherwise we'll be here forever and a day. Yeah, okay, we'll try that one. File, new. Okay, try that one. File, application project. It should show the list. It should show it. I think it's just because this a lot of messing about with this workspace and such like now. So I will switch back to the live one. Yes, that's the way to do it. Follow the instructions. Don't get confused talking like I did. Follow the instructions. Do the build for the live. Build the platform project first, and then you build the application project. But anyway, once you've gone through this, you can create a MicroBlaze project base, just like we had. Maybe actually you need to compile it first. Maybe that was yes, you need to compile it first. Of course, I'm being silly. You need to compile it before it can see it. Yeah. You need to build it before you can see it in Vivado. Yes. You can't, for some reason, this one won't. So in there, you can create a new application. In fact, we can create a new application. In fact, let's go back and do that now. I've realized the error of my way, because it'll take 2 seconds. We're getting good at switching backwards and forwards. So if we do this and then we build it here, when we hit that build hammer here, it'll create the project, and then we can go file application project, and I bet it appears now. MB live. Well, look at that. So we can go next. We can give it a name. What was the name we used again? Design 1. Sensor app. See now it's running here. Click on next, and this time we should have a list. I see that we've got a list of applications. We're going to go with the Hello World program first. I always like to start using the Hello World template initially, and just to see what it does. So now we have, where's my mouse gone? Now we have a simple project. We got there in the end. Thank you for bearing with me. We have a simple project. It's just got look at that. The world's most complicated project. It's just got a simple Hello World project in it. If we build this, we find out that my antivirus is still on. So we're going to quickly turn my antivirus off. So we see this gets built, and we can see it down the bottom. We've got a build and a file. So all we want to do now is we want to run it on our board, right? So we can do this very simply by coming in here and setting up a new configuration. So we need to set up a new configuration, debug configuration. We're going to do a TCF. So we're going to connect to the TCF framework on the processor. And this should be relatively simple to do. We're going to click TCF, new application. We're going to click this button here to have launch a new configuration. That's going to open this dialog box. Now, the key thing for this is we're connecting to Linux. So we're not going to download this over JTAG or anything like that. This is going to connect over the Ethernet and connect and do the debugging over Ethernet. So the first thing we need to do here is we need to go to the connection and do new. And we're going to call this one, we'll call this one sensor, for example. I'm going to set this as the default target, and then we're going to do 10.10.30.13, I believe was the IP address. And we'll do test connection. And we'll see then that it's gone away over my network, and it's talked to the kernel that's running on the RT board that we've currently got, and said, are you up and running? Can I connect to you? Can I download software? Do you have a TCF framework running? And it does. So with that, we can click on OK, and we can click on OK. So we've got the sensor there. We've got the project here. Now, the project's going to download. We're telling it where our path is, the debug, the sensor app. There's a remote path and the local path. Now, these are kind of by default. These are kind of set up for... They're kind of set up for assuming that you've got SD cards and such like on there, or non-volatile memory. I'm going to pull that over there for a second. I'm going to do this, and I'm just going to hit enter here, and I'm going to do PWD. Yeah. And what I'm going to do is I'm going to set this to run essentially in the home directory. So we're going to do /. home / PetaLinux. And then we're going to just change this one here to / home / PetaLinux. We're going to apply that. So but basically what that means is this is the location on our target that it can actually download the ELF to and actually run the ELF from. Once we've got that, we're all good to go. So I'm going to hit debug. And like magic, it goes across the system, it runs, it downloads, we're all running on the system. If I go here, if I just pull this across now, and I apologize that it's a little slow, a little small on this screen, but if I do ls here, you can see this, it's downloaded the sensor app.elf into the onto the board. And if we run this, single step over it, we'll see we get a terminal out here from our process terminal saying, hello world. Excellent. We've now got Vivado all up and running. We've built a MicroBlaze, we've built some software, we've put it on there. Let's create a little bit more of a serious application, shall we say? And let's go to the software application. And what I'm going to do is I'm going to go back to the design element here. We're going to do A on this and delete this. Do A here, and I'm going to copy and paste in the code from the GitHub repo that we have, and here we can see it's in the wrong folder, in the wrong file there, and here we can see it gets a lot more complicated now because we're pulling in standard libraries. So in this instance, the standard out is going to the TCF connection. If we run it, actually, if you run it on the, if you run it just from the directory where it's been downloaded over the terminal in the UART terminal over our on our Linux machine, it'll pop up hello world over that terminal window as well. So the standard out is the TCF framework and whatever it's been connected to. So what we've got now is we're going to run a simple application. We're going to pull in a lot of the libraries that exist for embedded for the Linux side of things. So we're pulling in IO control, we're pulling in the types. Importantly, we're pulling in this here, the SPI-dev.h. And all Linux is, it's really when we're working with things, it's kind of like you open a file, you do some things with it, you read or write from the file, and then you close it. So it becomes nice and easy. So it's cross-compiling on a Windows machine. So this Vitis installation is on a Windows machine, and it's compiling using GCC for it, and then it's just downloading it over there. Yeah. So this is the one benefit. So I didn't put a sysroot in this. You can define the sysroot if you want, but because this is just using really standard basic libraries, it's all within the ARM GCC toolchain that's installed with Vitis when you put it in there. And Jason, yeah, it's much easier to do this because now you can do single step in, and you can do all sorts of things, inspection, watching, and it's just like a software. It's just like it's accessed over JTAG, but it's not sat on the bench next to you. It happens to be in a lab or somewhere. So we can pull this. So you can see here, I'm calling through the SPI device. And if you remember, the SPI device was mapped under dev, SPI dev 0.0. I'm doing some basic setup here. So I'm setting up, so I want to do a 32-bit transaction, the speed of my transaction, the SPI mode I want to use. And then I'm setting up a simple buffer to do the SPI transmit and the SPI receive. In this case, I don't do any SPI receiving because the chip doesn't have an SPI receiver on it. So this is just doing it from the standard Vitis installation. So I've not gone fiddling with any GCC or anything like that. I've just installed Vitis direct from AMD and run this through. Yeah, so I'll give it a try, Brian, because it should work. This has been working really nice for me, and I've done maybe half a dozen webinars recently with PetaLinux based around it, and it's all kind of works okay. So what we've got then is we're opening the SPI element. So we're opening the SPI device. I'm asking if I can read or write that SPI device, because sometimes this number gets changed for a particular one. And then I'm setting up the SPI read and write modes. I'm setting up the bits per the write bits per word, the read bits per word, the max read and write speed. And then I'm basically writing data in. There's an ADC on this, so I'm using, where's it gone? I'm using the PMod DA4 on this, which has a analog devices AD5628 device on it. So I read the data sheet for the AD5628, and then I created some commands that I want to send across to over SPI to enable it and send data out. So, for example, here I'm telling it to enable sampling, so it's getting ready to start its sampling, and then I'm sending the message across and saying whether I can do it or not. Once we've done that, I'm sending some other messages across to pre-configure the tool, to pre-configure the ADC, and then once we get into a loop, all I'm doing is I have a count. I'm splitting that count into a couple of words, and then I'm writing that out to the DAC. So we're enabling we're opening the SPI, we're configuring the SPI, we're then using the opened SPI channel in Linux to talk to the DAC. We're configuring the DAC, and then we're writing some data out. So if we compile this, we should then be able to debug this, and we can use the same debugger as before, I hope. Yes. And we'll see it runs down, and I'll single step it through a few things, so we can see it's running through here. We can step through the terminal. If we want, we can put a breakpoint in here, and we can run it to the breakpoint. We can single step over that, and hopefully, luckily, it works. Now, if I pull up the waveforms, so this is the DAC as it currently stands. The output are connected to the oscilloscope. The oscilloscope's analog discovery that I can see over here. If we then just run the rest of this code, what we see is the data starts running and coming through on our oscilloscope as the ramp data is put there, and we see our application starts running. If we want to stop it at any point, we can insert a breakpoint maybe, and it hits that breakpoint and it stops, and we can go and inspect everything. And that pretty much brings me a few minutes before the end to the end of what I wanted to kind of talk about today, and show everything. Is there any questions that people have got? I see they've actually put some stuff in the questions. So yeah, somebody was asking actually if you can possible to work with FreeRTOS on the Zinc 7000 that uses two processors. Yeah, you can put the FreeRTOS on one processor and run it, or you can put it on both processors depending on how you configure it and run it. You can even have them running in what's called OpenAMP, where you have Linux running on one core and FreeRTOS running on the other, and that's there. I'm not sure. Somebody was asking about ISO 26262. I'm honestly not sure if PetaLinux is certified for that. I'll take that and I'll go away and find out and let you know. And then somebody was asking about if it's easier and faster to have separate Ubuntu VirtualBox to build the image. VirtualBox Ubuntu will work. I did that for many years before I decided I was going to build a Linux machine. So that's. But yeah, you can do it either. You can do it either way. Somebody's just said why question mark. What's the why question mark? Yes, so somebody wanted the XADC and drivers. So I said, this is a good point. I said about my blog, and I would go and get you some links. So, ADIUVO. If there's any questions, please think about them think and put them in the blog, and I'll try and do that. IIC. IIC. So let's go back and I'll get them. So the link for the recorded link won't be available until Zahid. I don't know if there's a safety critical version of PetaLinux that's been certified. It's not something I'm aware of. So where did I specify the correct PMOD port? So that was when I did my pin out. So when I did the pin allocation in Vivado with the XDC file, I didn't show it in this lab at the time, but I opened the schematics for the board, for the RT board that I was on, and then traced through the PMOD signals through to the FPGA pins, and then added those in there. I'm curious to know why you said question mark, why question mark, question mark, question mark, what that was in relation to. So don't leave me hanging before we hang up if you're still here. So there's some blogs coming through. I'm going to put them in here. There is one there on how to get things to auto start up and auto run. There is some more coming through if you bear with me a second. So here is one on PetaLinux. Here is one on UIO. And here is one on software applications with UIO. And then where did I do this blog for? This one, IIC. No, it's not IIC. XADC. IIO. So I'm afraid I don't have any blogs directly for sort of like doing a specific thing like the FMC comments. You'd have to take the concepts and the blogs that I've written, I'm afraid, and sort of run through with those. There's one there on how to use the rest of it. But yeah, it's been fantastic to have you all here and all listening to this. I hope you've all enjoyed and learnt a lot about it. There's obviously keep an eye on my blog and my Hackster, and see what we can do. And if you've not voted yet already, please vote in the polls and let me know what I want to do. I've got to do two more. I have to do two more of these in the next couple of months. I'm curious as to what people want to do. I'm on sort of things like timing constraints, AI, sort of good design techniques for FPGAs. You will be able. You will be able to find my the video later on my YouTube channel at the very least, and I'll try and link everything to it. And you can find that here if you're not familiar with it. How's the weather? The weather today's not been too bad, actually. It's still a bit miserable and horrible. Let's take a look. So by the winner by default on this one seems to be, I'm going to take a screenshot of that because I'm not sure if this is available to me afterwards on the results of the quiz. So let me ask a quick question as well before everybody goes. So I've just added a poll. If you're still around, I'm curious if you would go and having done this, if you'd used Petalinux, if you answered the poll at the beginning where you said no, I'd never used Petalinux on a MicroBlaze before, and people said, majority of people said no. I'm dead curious now if that's changed your mind at all. Thank you all for coming and listening. I'm going to stop sharing my screen now. So is there a page that's got everything on it? The best page to find everything that I do is to go to my company website, and that you can find pretty much links to everything that you need from there. Thank you. I'm glad you all enjoyed it. I'm sorry we had a couple of weird things along the way, but I really enjoyed it. So I'm going to go and I've been teaching an FPGA design class every night this week, and I think I've seen a few of them actually attend so far today. So I'm going to go away and prepare for the FPGA for the next session of the FPGA design class tomorrow evening, and maybe even find a soft drink or something. I'm going to look at that poll though and see. This is good. So keep voting. Before you leave, go vote in the poll so as I can tell everybody how great I am at teaching about Petalinux and how everybody wants to use it. And everything, like I say, everything will be updated onto the everything will be updated onto the GitHub repo and everything this evening if I've missed anything from it. So the video link, it will be up. If you look up in the chat, it will be on my. Well, you can always come back here and watch it because it'll be available here. But you can see it at there'll be definitely a link on my YouTube channel, and you'll be able to find it from my website as well. So if you go to my website, you'll see a thing on the top called workshops. If you go to the workshops, there's a drop-down menu, and that gives you access to every workshop I've done around AMD and other FPGAs, and you can generally links you to the GitHub and to the YouTube, so as you can go see it. You can go see it all from there. But yeah, thank you very much. If you're still here, just go vote on that poll for me, would you, for a couple of minutes, and just let me know what's going off, what your thoughts on it are, and then I'll wrap it all up, and I'm going to go power these machines down. They've worked quite hard today, and then I shall go home. Yeah, Brian, sorry. Yeah, you were going to ask me. So the Korea carrier, actually thinking about it, I don't think we did do LVDS signals on this, but I think I can test. This is quite a funny one. So this Korea carrier card actually has a MicroZ slot on a MicroZ thing on the bottom. So it actually plugs into MicroZ board. So I think I can plug it on and test it on LVDS if you had any questions in mind. My email address is on the front of that, so if you want to talk about it, just ping me an email, and we can do it. And like I say, if anybody else has not got it, then my email is adam@adiuvoengineering.com. And generally, I do reply to emails that everybody sends me. Sometimes I get a little bit busy, so please, if I don't reply, don't feel rude and just email me and say, "Oi, Adam, why haven't you answered?" And I'll then reply. Sometimes I have them open with like half-written replies for a while before I get around to it because we're quite busy. But yeah, ping me that stuff. Ping me what you want, Brian, and I'll take a look at it and we'll see what we can do. Right. With that in mind, I am going to end the webinar, and we'll take it from there, and we'll see it. And we'll see you next time. in a couple of months. I'll let you know what the next webinar is. There's one coming up on. I'm doing one for AMD on Versal. If you're not familiar with Versal and you want to learn about the Versal devices, it's not going to be quite as in depth as this. It's just like an hour's long talk and discussion about Versal and the architectures and stuff. And that's going to be coming up at the end, towards the end of May. We're going to be doing that one. Have a good evening all. I'm going to shut this event down now. So thank you very much for coming, and I will speak to you all soon.